Welcome, curious minds, to the deep dive. We pull out the most vital insights from, well, all sorts of fascinating knowledge areas. And today, we're plunging into something huge, a concept that didn't just tweak our view of the universe, it completely shattered it, and then put it back together differently. Just imagine, for a second, that the clock on your wall, the space you're in right now, even the very idea of now, what if it isn't fixed? Not universal.
It's a genuinely mind-bending thought, isn't it? When we hear relativity, people often think, maybe that famous picture of Einstein. But the real depth, the truly profound part, isn't just the math. It's the question it forces us to ask. What if everything you assumed was absolute time, space, even simultaneity, is actually relative?
Exactly. That's the heart of this deep dive. Albert Einstein wrestled with that. And in doing so, he didn't just rewrite physics. He fundamentally changed how we, as humans, relate to reality itself. So we're going to trace this idea from its first whispers right up to its impact today. We'll look at the history, the psychology, how different cultures saw it, even some of the myths that stick around. Settle in, because this might just change how you see your own place in this, well, incredibly dynamic cosmos.
Yeah, and to really grasp the shift Einstein brought about, we kind of need to picture the world before him, scientifically speaking. For centuries, you had the Newtonian universe. It was dominant, a comfortable, predictable order. Newton saw this clockwork cosmos, absolute time, ticking the same for everyone, everywhere, and absolute space, like this invisible, unmoving stage where everything happened. It was elegant, predictable, and it worked incredibly well for explaining, well, pretty much everything from falling apples to planets moving.
And it really did work for ages. That predictability, it powered centuries of science, of engineering. But then, late 19th century, you start seeing these little cracks appear, especially around light. The big one was the Michelson-Morley experiment in 1887. They were looking for this thing called the luminiferous ether.
Right, this hypothetical substance they thought light waves traveled through, like sound through air.
Exactly. But the results were just baffling. No matter how the Earth moved, the speed of light always seemed the same, constant, which completely contradicted how we thought velocity should add up. It was a real crisis for Newtonian physics.
It really was a major puzzle. And this weird constancy of light, it set the stage, intellectually, I mean. You had thinkers like Hendrik Lorentz, Henri Poincaré. They were already working on maths that hinted maybe space and time weren't so absolute after all, building pieces of the puzzle.
But then came Einstein, a young patent clerk. Amazingly, 1905, his annus mirabilis miracle year, he published several papers, and one, the special theory of relativity, just took a radical approach. Instead of trying to fix the ether problem, he just got rid of it, said we don't need it. His theory stood on two postulates, simple but revolutionary. One, the laws of physics are the same for all non-accelerating observers.
Okay.
Seems reasonable enough.
And two, the speed of light in a vacuum is the same for all non-accelerating observers. Always, no matter how the source is moving.
And that was the bombshell. From those two ideas, absolute time and absolute space just dissolved. Concepts like time dilation, time literally slowing down for moving objects compared to stationary ones, and length contraction, they became real consequences. It was an earthquake for physics. Then 10 years later, 1915, he expanded it. General theory of relativity. This brought in acceleration and gravity. And his idea for gravity was just breathtaking. He said it's not a force pulling things, it's the curvature, the warping of space-time itself, caused by mass and energy. The universe wasn't a static stage anymore. It was dynamic, interwoven. Matter tells space-time how to curve, space-time tells matter how to move. It's such an elegant, almost poetic reconception of gravity. So, okay, the physics is one thing, mind-bending, sure. But what happens when an idea like that, time isn't fixed, space isn't fixed, leaks out into the wider world? How does that hit us? Psychologically, societally.
Now that's where it gets really fascinating. Think about it. For thousands of years, human experience was built on this bedrock, a shared clock, a fixed backdrop, our language, our rituals, our sense of community, all anchored in common time. So when Einstein's ideas started to filter out, even simplified, it was, well, deeply unsettling for a lot of people. It poked at common sense reality. Psychologically, it introduces this kind of existential ambiguity. If your now isn't the same as my now, what does that mean for shared history, objective truth, even just experiencing an event together? It raises these deep philosophical questions too, doesn't it? About free will, causality, if time itself isn't this simple straight line for everyone.
Wow, yeah, you can see how that might create a kind of societal cognitive dissonance. The solid ground you thought you were on suddenly feels a bit wobbly.
And it meshed, in a weird way, with everything else happening in the early 20th century. You had world wars, massive technological change, Freud and Jung digging into the subjective unconscious. Relativity, in a sense, almost gave a scientific okay to the feeling that reality was maybe less straightforward, less predictable than we thought.
That's a really interesting parallel. Freud uncovering hidden drives, Jung exploring archetypes, while Einstein's showing the physical universe is also more complex, less absolute. Do you think Einstein's work directly fueled that cultural shift? Or was it more like science just reflecting a broader questioning of absolutes happening everywhere?
I think it was probably a bit of both, a potent interplay. It certainly encouraged new kind of, let's call it epistemological humility. The idea that what you perceive depends fundamentally on your frame of reference. That became a powerful metaphor way beyond physics. It subtly nudged along that idea that my truth might differ from your truth, not just emotionally, but almost structurally, because our reference frames are different.
So how did that play out sociologically? Did it lead to fragmentation, like everyone having their own reality? Or was it maybe liberating somehow?
Well, both, I think. For some, hearing that even science didn't have the absolute truth could maybe feed into relativism, feeling adrift, maybe even nihilism. But for others, it could be incredibly freeing. It challenged old authorities, rigid thinking. It encouraged a more nuanced view, maybe less black and white.
It really makes you think about the art world then. Picasso and Cubism, literally showing multiple viewpoints at once, or James Joyce in literature playing with subjective time. It feels like the whole culture was moving that way.
Absolutely. The science provided this powerful intellectual framework for a shift that was already stirring culturally. It's hard to draw direct causal lines, of course, but you feel those echoes of relativity in the move away from grand universal narratives towards individual experience, in deconstructionist thought, in emphasizing subjective interpretation. It subtly but profoundly reshaped how society wrestled with its own sense of reality. And it's also worth remembering that ideas about time and space weren't uniform across the globe even before Einstein. Different cultures had vastly different conceptions. So how did relativity land, when it encountered these diverse pre-existing views? Especially comparing, say, East and West.
That's a great point. It shows how science always interacts with culture. In the West, especially after the Enlightenment and the Industrial Revolution, there was this really strong focus on linear time. Time is progress, marching forward. Efficiency, schedules, history as a straight line. Newtonian physics fit that perfectly. Predictable, measurable, absolute. So Einstein's fluid time, that was a major shock. It challenged that deep-seated sense of order and predictability. The twin paradox, for instance, one twin aging slower, it's physically true but feels so deeply wrong based on our everyday Western assumptions about time.
But then you look east, and in many traditions think of Hindu yugas, those vast cosmic cycles, or Buddhist ideas of impermanence and interconnectedness. Time was often already seen as cyclical, or maybe less rigidly linear. So while the math of relativity was new, the concept of time being fluid or context-dependent might have felt, well, maybe less alien. Perhaps it resonated more intuitively with frameworks that already saw reality as dynamic, interconnected, not so fixed. Fritjof Capra wrote a lot about this, didn't he? The parallels between modern physics and Eastern mysticism.
Yeah, the Tao of physics. He argued that quantum mechanics and relativity often seemed closer to ancient Eastern wisdom than to classical Western thought. And you can see that maybe in some indigenous cultures too, where time is often understood more relationally tied to seasons, natural cycles, community events, not just an abstract clock. Maybe for them, the idea that time could be experienced differently depending on context wasn't quite the existential bomb it might have been for highly standardized Western societies.
It's a fascinating thought, isn't it? Did some cultures already have the conceptual hooks that made relativity feel less like a revolution and more like a confirmation of something they already sensed? Think about sayings like everything is connected. Suddenly, with space-time curvature, that takes on a new, almost literal scientific dimension. Or the Buddhist idea of impermanence, maybe that resonates differently. When you learn even space and time themselves are dynamic, not fixed backgrounds, it really shows how science gets filtered through our cultural lenses.
Okay, so we've talked theory, we've talked cultural impact, but let's bring it right down to today. How does this incredibly abstract theory actually show up in our daily lives? Is it just for physicists? Or does it touch us?
Oh, it touches us constantly, often without us realizing. The single biggest example, GPS, your phone's map, your car's navigation.
Right, you hear that GPS relies on relativity. But how exactly? The satellites are moving fast, they're further from Earth's gravity. How much difference does that really make?
A huge difference. Those satellites are orbiting at about, 8,700 miles per hour? That triggers special relativity. Their clocks tick slightly slower from our perspective due to their speed, but they're also in a weaker gravitational field than we are down here. And general relativity says time ticks faster in weaker gravity.
Ah, so you have competing effects.
Exactly. And you have to calculate both effects precisely. The gravity effect is actually stronger than the speed effect for GPS satellites. If the system didn't account for these relativistic time differences, the errors would build up incredibly fast. We're talking several miles per day. Your GPS would be useless.
Wow. So every single time I use Google Maps or Waze, I'm relying on Einstein's equations working correctly up there.
You absolutely are. It's relativity in your pocket, guiding you around. And beyond GPS, it's fundamental to cosmology. Our whole understanding of the universe's origin, its expansion, black holes, the Big Bang, it all rests on the framework of general relativity.
What about cutting-edge science? Does it play a role there?
Definitely. Particle accelerators, like the Large Hadron Collider at CERN, they smash particles together at incredible speeds, close to the speed of light. And at those speeds, you directly observe relativistic effects. Particles gain mass, their lifespans get extended because time slows down for them, time dilation again. Scientists have to account for these effects perfectly to even design the experiments, let alone interpret the results. You couldn't do modern particle physics without special relativity.
So it's like this invisible scaffolding for both the biggest scales cosmology and the smallest particle physics.
Right. And then there's popular culture. It gets misinterpreted a lot, sure, but relativity is still a huge source of inspiration. Think about movies like Interstellar, with its dramatic portrayal of time dilation near a black hole, or countless sci-fi stories about wormholes, warp drives, even the idea of alternate realities or multiverses. It often borrows a little something from the notion that reality isn't quite as fixed and absolute as we used to think.
So yeah, from finding the quickest route to work, to understanding the universe's fate, to inspiring science fiction, Einstein's ideas are woven into the fabric of our modern world. It's a constant reminder that our intuition about how things work is often just the tip of the iceberg.
Now, whenever you have a theory that fundamentally changes our view of reality, like relativity did, you're bound to get misunderstandings, controversies, myths building up around it. What are some of the big ones we should clear up?
Yeah, there are definitely a few. Probably the biggest, most common one is the idea that relativity means everything is relative. Like in a philosophical sense, no objective truth, anything goes.
Which is a huge misunderstanding, isn't it?
A massive one. Relativity in physics means that measurements of things like time and distance depend on your frame of reference, your motion. And this is crucial, the laws of physics themselves are absolute. They're the same for everyone.
Exactly. The speed of light in a vacuum is the ultimate constant in special relativity, for instance. It doesn't change depending on who's measuring it. So the theory doesn't destroy objective reality. If anything, it reveals a deeper, more interconnected objective reality governed by consistent laws that relate different viewpoints. It's about the relationships between frames, not chaos.
Right. Another big misconception is about time travel. People hear time dilation and think, great, time machines.
Yeah, the whole jumping into the past or future thing.
Well, time dilation is real. Time passes differently for observers in relative motion or different gravitational fields. So traveling into the future is sort of possible in a limited way. If you zipped off in a spaceship near light speed and came back, less time would have passed for you than for people on Earth. You'd have effectively jumped into their future. But traveling back into the past, that's generally considered impossible by current physics. It leads to paradoxes like the grandfather paradox and seems to violate causality. So no DeLorean, unfortunately.
Oh, okay, what about immersive? People often just link it straight to the atomic bomb.
And while it was key to understanding the energy release in nuclear reactions, its meaning is much, much broader. It's about the fundamental equivalence of mass and energy. Mass is a form of energy, a very concentrated form, and energy can be converted into mass. It's a basic principle of how the universe works, far beyond just bombs.
Were there actual controversies back when Einstein proposed these ideas? Did scientists push back hard?
Oh, absolutely. Especially initially. There was significant skepticism, even hostility from some established physicists. They were deeply invested in the Newtonian worldview with its absolute time and space.
Einstein's ideas seemed counterintuitive, philosophically troubling to some. It took time and evidence for general relativity especially to gain acceptance.
The real turning point was that 1919 Eddington expedition during the solar eclipse.
The one that measured starlight bending around the sun.
Exactly. When Eddington's measurements confirmed Einstein's prediction that gravity warps space-time and bends light, it was huge news. It made Einstein a global celebrity and really cemented the theory's place.
So it wasn't just accepted overnight, it had to overcome inertia and be proven by observation.
Definitely. And even today, the controversies aren't really about whether relativity is wrong. It's incredibly well tested. The debates are at the frontiers. How do you make general relativity work with quantum mechanics?
These aren't arguments against relativity itself, but about how it fits into an even bigger, more complete picture of the universe. That's where things like quantum gravity, string theory, loop quantum gravity come in, trying to build that unified picture.
So even though Einstein's theories are foundational, science keeps pushing, right? What are the big ideas trying to go beyond relativity, or maybe integrate it into something larger?
That's the nature of science, always building, always refining. And yeah, the biggest challenge, the biggest push beyond Einstein right now is trying to reconcile general relativity with quantum mechanics. Like we said, they're the two pillars of modern physics, incredibly successful in their own domains. GR for the big stuff, gravity, cosmology, QM for the tiny stuff, particles, forces.
But they just don't mesh well together, do they? What's the fundamental clash?
Well, the core issue is how they treat space-time. General relativity sees space-time as smooth, continuous, like a rubber sheet that gets bent. Quantum mechanics, when you try to apply it to gravity, suggests that at the very tiniest scales, the Planck scale, space-time itself might be jittery, quantized, foamy, not smooth at all. This conflict becomes a real problem when you try to describe extreme situations like the very center of a black hole or the instant of the Big Bang, where you need both theories to work together. And they don't. That's the driving force behind things like string theory and loop quantum gravity.
Okay, so string theory, what's the basic idea there? Trying to smooth things over.
Sort of. String theory suggests the fundamental constituents of reality aren't quite like particles, but tiny, vibrating, one-dimensional strings. And the different ways these strings vibrate correspond to different particles and forces, including gravity. It inherently includes gravity in a quantum framework, but it usually requires extra dimensions of space, curled up really small, which is a pretty wild concept itself.
Okay, extra dimensions. And loop quantum gravity to use strings too.
No, it takes a different path. Loop quantum gravity tries to directly quantize space-time itself. It suggests space isn't continuous, but is made of discrete chunks or loops at the Planck scale, like pixels on a screen. So space-time itself has a fundamental granularity. Both theories are trying to bridge that GRQM gap, just coming at it from different directions. Very complex, very cutting-edge stuff.
And then there's the whole mystery of dark matter and dark energy. How do they fit in? Are they challenges to relativity or predicted by it?
That's interesting. They're more like consequences or puzzles highlighted by general relativity. When astronomers observe how galaxies rotate or how the universe's expansion is accelerating, the amount of visible matter and energy just isn't enough, according to GR, to explain what we see. So GR predicts there must be something else there. Dark matter providing extra gravity and dark energy driving the accelerated expansion.
But we haven't actually found these things directly yet.
Not directly, no. We infer their existence from their gravitational effects, as described by general relativity. So, in a way, these mysteries are pushing the boundaries of GR. Are they new forms of matter and energy within the existing framework? Or do we need to modify GR itself at cosmic scales? That's a huge area of research. It really shows how powerful Einstein's framework is. It leads us to these profound questions about the 95% of the universe we apparently can't see.
So Einstein laid the groundwork, but these new theories and mysteries are like adding extensions or maybe finding hidden rooms in the cosmic house he designed, still building on that foundation.
It's easy to get lost in the abstraction, but let's ground it again. Can we look at a few really concrete examples, case studies where relativity isn't just theory, but something observable, testable, maybe even engineered?
Absolutely. We already touched on the 1919 eclipse, which was maybe the most dramatic early proof. Einstein predicts light bends near massive objects because space-time is warped. Eddington goes, observes stars near the eclipsed sun.
And finds they appear shifted, just as predicted.
Exactly. The amount of bending matched general relativity's calculations. It was huge news, made Einstein famous overnight. A direct, visual confirmation that space isn't just empty background, it's an active participant.
A defining moment. What about something more modern, maybe technological, besides GPS?
Particle accelerators, definitely. Take the Large Hadron Collider at CERN. They accelerate protons or ions to, what, 99.9999999% the speed of light? Something crazy like that.
At those speeds, special relativity isn't optional, it's essential engineering.
Totally. The particles gain enormous mass, just as EM2 implies when you pump energy into them, and their internal clocks slow down dramatically due to time dilation.
You see unstable particles like muons, which should decay in microseconds, surviving much longer journeys around the accelerator ring because time is passing slower for them.
You have to factor all this in perfectly to make the beams collide where you want them, to interpret the debris. The whole multi-billion-dollar facility relies on relativistic calculations being correct.
That's a fantastic example. It's relativity as a practical tool for discovery, and cosmically.
Black holes are the ultimate showcase for general relativity, aren't they? Regions where gravity, the warping of space-time, is so extreme that nothing escapes.
Einstein's equations predicted their possibility long before we had strong observational evidence. And now, with things like the Event Horizon Telescope actually imaging the shadow of a black hole, that silhouette, the way light bends around it, it's another stunning visual confirmation of general relativity working in the most extreme environment imaginable. So from tiny particles whizzing around a tunnel to the edges of black holes billions of light years away, relativity is right there, describing what's happening. It's not just equations on paper.
Not at all. It's woven into the fabric of reality, from the smallest scales we can probe to the largest structures we can see. Pretty amazing how abstract math connects to tangible reality.
So we've covered so much ground. Looking back and looking forward, what are the really critical reflections we should take away? What are the big lingering questions or maybe even future challenges stemming from relativity?
Well, the biggest unresolved question has to be that unification with quantum mechanics we keep mentioning. How do we get a theory of quantum gravity? Without it, the Big Bang singularity, the inside of black holes, they remain fundamentally mysterious. Cracking that is probably the biggest challenge in fundamental physics.
And the answer could completely change our concept of space-time at its most basic level.
For sure. Then there's the philosophical side. We still grapple with what relative time means. If there's no universal now, how does that impact our ideas about causality, about the flow of time, maybe even free will? Physics raises these questions, even if it can't answer them alone.
It definitely forces us to accept that our everyday intuition about time and space is just limited, an approximation that works well locally but breaks down in extremes.
And looking ahead, new observations will keep testing relativity. Gravitational waves give us a new way to hear the universe, probing cosmic collisions, precision cosmology, studying the early universe. These could reveal tiny deviations from GR, hinting at new physics.
What about the really sci-fi stuff? Warp drives, wormholes, manipulating time. Any realistic prospects there based on relativity?
Well, relativity does allow for some weird possibilities in principle. Time dilation is real, so future travel is theoretically possible, just not practical yet. Things like traversable wormholes or warp drives often appear as valid mathematical solutions within general relativity, but they usually require things like exotic matter with negative mass or energy, which we've never observed and might not be physically possible.
So while mathematically interesting, they remain highly speculative.
Highly speculative, yeah. Fun for sci-fi and important for theorists exploring the limits of the theory, but not something we expect to build tomorrow. But I think the key takeaway is that Einstein didn't just provide answers, he gave us much better, deeper questions. He showed us a universe that's stranger, more elegant, and more interconnected than we'd ever guessed. The quest to fully understand it, within and beyond relativity, is far from over.
It really has been an incredible journey today, hasn't it? Starting from that old clockwork universe of Newton and arriving at Einstein's dynamic, warped space-time. It's so clear that relativity is way more than just physics. It's shaped our culture, our thinking, our technology.
Absolutely. For me, the biggest thing is just how an idea born from math and physics can seep so deeply into how we understand reality itself. Questioning the absolutes of time and space, it's humbling, really. Makes you realize the universe doesn't have to make intuitive sense to us.
Yeah, and I love the paradox you mentioned earlier. A theory called relativity ends up pointing towards deeper, more fundamental universal laws, the consistency of physics, the speed of light. It's not about randomness, it's about a more complex underlying order. Our perspective is limited, sure, but the universe has this incredible elegance.
That's a great way to put it. It leaves you with this image of a dynamic, interconnected cosmos. So next time you look at the night sky, or maybe just check your GPS, take a second to think about that silent, powerful influence of relativity shaping everything.
And maybe the final thought for everyone listening is just that. The willingness to question what seems obvious, what feels absolute. That's what really stretches our minds. That pursuit of understanding might be what actually expands the fabric of our shared reality.
Thank you so much for joining us on this Definitely mind-bending deep dive. Until next time, keep exploring, keep asking questions, and keep weaving together your understanding of this amazing universe.